Right.
Third time's the charm.
Oh. It's better than a no. Is that where you're sitting? I feel like this is going to be a distraction. No, but you can sit there.
He's within striking. He's gonna win.
Oh, now the rest of you show up.
Sorry.
Well, some of the rest of
He
you.
stole your spot.
Okay. So,
That man, he's questionably late.
okay.
I'll be serious. Yeah.
Okay, so the essential thing to know about really any time-stepping methods that I highlighted last time is that consistency plus stability equals convergence. Now, last time I covered these concepts for one-step methods, and so today I'll do the same for multi-step methods, because the way you verify whether a method is consistent or stable is completely different for one-step as opposed to multi-step. Now, as far as what these things actually mean, a quick review of that. Okay. Is that consistency means that as h goes to 0, the error that's incurred during a single time step also goes to 0. And we're not just interested in whether the error from one time step goes to 0, but at what rate. So if it goes to 0 at a rate of order h, that's first order accurate. H squared is second order accurate, and so forth. Okay, so that's a criterion for consistency. First, the definition of consistency. Stability simply means that a small change in the initial data means a small change in the overall solution. So over time, and that's important because whatever error is incurred during one time step, if a method is stable, that means that that error is not going to suddenly be amplified to a large degree over subsequent time steps. So we really need the two of these together to make sure that the overall error incurred during the computation to go from initial time to final time does not get out of hand. So convergence is that as h goes to 0, the numerical solution approaches the exact solution. Okay. And checking whether the numerical solution actually converges to the exact solution is very difficult to do using the definition of convergence directly, and that's why we have consistency and stability. It's much easier to verify these two things. So then someone was nice enough to prove that these two implied this, which makes things a lot easier for trying this with whatever method you're given, whether it's a Runge-Kutta method, one-step method, or say an Adams-Bashforth method, which is a multi-step method. Okay. So last time I went over, here's how you check consistency for a one-step method and also stability. So now we're going to forget about that and take up these same things for multi-step methods. Before I move on with that, so now people are starting to get their oral finals scheduled. That's good, but still not many. I think 4 people have. Yeah, that still leaves a lot. I'm only aware of one person choosing the coding option. Um, so, um, so for the rest of you, try to figure out which one you want to do. The coding option is posted. Because since next week I'm not going to be around for much of a week, just a Thursday and Friday, and then there's still plenty of opportunity during finals week as well. Because my schedule, I won't be around to Monday, but Tuesday, Wednesday, Thursday, there's still plenty of opportunity. Okay. All right. So for multi-step methods. First, consistency. Okay. Now it's actually easier to talk about this from point of view of we restrict ourselves to Adams methods because they all have this particular form that's a little easier to work with, regardless of whether it's the Adams batch form or Adams Molson methods. So if I review for you that where Adams methods come from, is the fact that we have y of tn plus 1 is equal to y of tn plus, so basically I'm writing the ODE in integral form. Okay. So now this relationship that I've written down here, this is exact. The exact solution satisfies this. So if we had a way of evaluating this integral exactly, we wouldn't need an approximation method at all. We wouldn't need time stepping. We would just do this. But unfortunately, we can't. So what Adams methods do is they approximate this integral using a polynomial that it's an interpolating polynomial that passes through these points. So Ti and Fi for I equals n plus 1 and n minus 1 and so forth, all the way down to n minus m plus 1, where m is how many steps are in a method, because a multistep method has m steps. Although I should mention, n plus 1 is only included in the implicit case. In other words, Adams-Moulton method. Otherwise, you're starting from n and backtracking from there. So, implicit method has one extra point. So, because we're using a polynomial interpolant to approximate this f here, that way we can evaluate the integral of that, at least, and that's where the Adams method comes from. I stepped through this 2 classes ago, and that's where all the betas come from. So what that would mean is the error, or I should say the local truncation error, is equal to 1 over h, because to approximate the ODE from this relationship, we'd have to divide by h. So it's 1 over h times the integral of, and I'll just write it informally here and then I'll work it out, the interpolation error. Okay, so whatever error you incur from approximating this f by a polynomial the interpolating polynomial, that's what you plug in, so that's what you integrate instead, and after dividing by h, just to conform to the definition, that's your local truncation error. So that's what you want to go to 0 as h goes to 0. Okay. Now, so what is that interpolation error? That's actually a last semester question. So in 460, 560, well, actually last semester there wasn't a 560 because there were no grad students. But in 460, the interpolation error was covered. So I'll just fill in what the formula is. Okay. And that would be, okay, make sure I get this right. Oh, whoops. For some reason I thought I had my textbook open on your computer.
I mean, you could.
Yeah, I could. But then I'd really be flipping back and forth a lot.
You're adulting and in grad school.
What? Oh, okay. You have an adulting folder?
Yes.
Okay.
Slowly working
Oh, okay.
bills and car notes in there. It's terrible.
Or I see if like something that's posted everywhere about how when you're
Adulting is hard, lame, overrated. Don't do it.
that
I'd like to second that.
that when you're an adult, then you find yourself looking for an adultier adult.
Yes.
Yeah. So then.
That's you.
Yeah. So then I realized.
You're adult.
I'm the adultier adult.
Yeah.
And like, okay. So.
They usually just go next door. Someone there's gotta be older.
So. Jeez. Okay. Where's this? Okay. So what we have here. First, I'll cover the explicit case. So that's Adam's Bashforth, and then I'll show how it's adjusted for the implicit case. So what we have is the nth derivative of f evaluated at some unknown point, squiggly, that's a time value, over m factorial, and then we have s minus tn, s minus tn minus 1, all the way to the last time value that we used, s minus t n minus m plus 1. So the integral of all that would give you the local truncation error. Now, fortunately, this can be worked out to a certain degree. Okay. So, because what we can do is
it y of s or y of squiggle?
y of squiggle.
That's what I got.
Okay. We can use the weighted mean value theorem for integrals. So this expression right here is always, well, let's see. S is between Tn and Tn plus 1. So, why do I have a, oh, I remember now, okay. So, that's always greater than or equal to 0 for the S that we're considering. Okay, so when that happens, okay, so this is a little talked about theorem. I think it actually never comes up in calculus courses unless I'm teaching it. And I think, but it's so useful. If you have an integral of a product, and one part of that product does not change sign, which we can confirm from this part here, then what you're allowed to do is you can pull out the other part. Now, it's evaluated at an unknown point, so this is only useful for estimating. And then you have the integral of the rest. And the thing is, that part can be worked out. because that has nothing to do with f. It doesn't have to do with any particular ODE. Now, what's more is you can now when I work through something like this in deriving Adams methods, it's possible to make a change of variable to make the integral simpler. So if I let u be equal to Tn plus 1 minus s all over h, then instead of integrating from Tn to Tn plus 1, we're integrating from 0 to 1. So what's possible to do is get a simpler expression for the error. Okay. Okay. Now, so using a change of variable, we still have the m derivative of f at an unknown point, m factorial, and then because of the change of variable, okay, we end up with h to the m. So part of that's due to the 1 over h, and the rest of it is due to the change of variable. I won't go through all those manipulations right here. So we get the integral from 0 to 1. We also have a factor of minus 1 to the m. That also comes from the change of variable. Because if you have s minus ti, but we have a change variable, u is Tn plus 1 minus s all over h. So if I take this and solve it for s is equal to Tn plus 1 minus minus UH. So what happens, let's see, do I have that right? HUS, yes. So that becomes T equals 1 minus UH, and then TI is equal to okay. Well, for now, I'll just fill in that. So what that becomes is n plus 1 times h minus u times h minus I times h. Well, h is in that whole thing. So it's h times n plus 1 minus I minus u. And u is going from, what is that?
It's his laptop.
What?
He's trying to mute it.
Sorry.
Okay.
He's trying to. He had it in his backpack, and it's just bleeping, bleeping, bleeping.
Okay.
He wants to join the party.
All right. Okay. So the thing is, the point is, we get a factor of we get a factor of h in each one of these. So that's m factors of h that gets pulled out. There's another h that comes into play from making a u substitution. They learned in Cal 2, but that cancels with a 1 over h that was out there in the beginning. So that's why overall we have a h to the m. Okay. So what we get as a result of this is n plus 1 minus I. Well, that's an integer because I goes from as an integer going from n plus 1 minus m all the way up to, or actually no, it goes from 1 to m. So once we simplify everything, what we have inside the integral is u minus 1, u minus 2, all the way down to u minus m. So in fact, if I let I go from 1 to m, something's wrong. That's sorry. This
I'm
is
writing in pen.
oh, what?
Nothing.
Okay. Okay. Oh. Right. Yeah, these are wrong. I goes all the way up to n, and then this is okay. So that's why these integers here end up going from 1 to m. After we simplify as much as we can. Okay, so this is the local truncation error, tau n of h. Now I've glossed over some things, so I don't expect you to see every detail of how this came from the original formula. But if you work through it doing the cal2 manipulations, this is what would fall out. So this is the local truncation error for an explicit or Adams-Bashforth multi-step method. And for an implicit or Adams-Moulton method, it's similar. We have m plus first derivative over m plus 1 factorial. And then I have h to the m plus 1 minus 1 to the m plus 1. So everywhere you see m, it changes to m plus 1. And inside here we have u minus 0, u minus 1, up to u minus m. And it's from this that you can see why an Adams-Bashforth method is mth order accurate, and Adams-Moulton method is m plus 1 order accuracy. It's because of the terminating polynomial being degree 1 greater. Okay. So that's how those formulas are arrived at. So for a particular Adams-Bashforth Adams-Moulton method, this integral can be worked out to a number. I won't do that here, but it's something that could be done for a particular example, or you can have software do it. So these formulas haven't worked out for all the many different Adams methods. I won't say all of them because there are infinitely many. But okay, so that's for an Adams method. But for a general multi-step method that can have whatever combination of alphas and betas, it's a much greater pain to deal with. So now a general multi-step method that what do you do? Okay, I need to separate this. Now, what you do is well, first the steps. You substitute the exact solution into a multi-step method. Now, this is what you do. That's actually what you do for local truncation error in general. You substitute the exact solution into the multi-step method. That's actually what I did, essentially, over there. Now, and then you simplify as much as you can, and that's your local truncation error. And then the second thing you do is you Taylor expand all your different y values, because you have y at different t values, tn plus 1, tn minus 1, and going backwards from there. And you expand around tn plus 1. Now, in a multi-step method, you have values of y, and you have values of f. way you handle values of f is that fi is actually f of ti y of ti, but that is equal to y prime at ti. So use the fact that y prime is equal to f for the exact solution. Then I Taylor expand y prime also. So you've seen it before with other cases where I have an f of ty. I'm doing a multivariable Taylor expansion, which is obnoxiously ugly. Even for a Taylor expansion, it's just worse. But not here. We rewrite f as y prime and then Taylor expand that. So we're only doing single variable Taylor expansions. And then what you do is you get a big mess, and this is all worked out in the book, so I won't repeat it here, is you group your expression by powers of h. Okay. Dang it.
Too soon.
I just missed. Like I actually saw it go black. Okay. All right. So what I'm going to do is, rather than go through all that monstrosity, which I'm guaranteed to screw up here in the middle of class, I'm going to show you the result of that and how you use it to check how accurate is a given multi-step method when it's not an Adams method. And it's kind of sad because I actually was going to do it, but time. Although in preparing to do it, I saw a typo, so at least I can make the book a little better. Okay. So what happens is I'm going to write down the coefficients of each power of h in there. So what we have is okay. Where'd it go? Okay. So the coefficients of h to the k are C0, C1, CK. So each CK is the coefficient of h to the k in this. All right, or actually h to the k minus 1. So I can give formulas for that. So C0 is just the sum of all the alphas in your multi-step method. And to refresh your memory, the general multi-step method has this form. Linear combination of y's on the left side, the coefficients are the alphas. And on the right side, you have h times a linear combination of f values, and the coefficients are the betas. So these c's are going to involve both the alphas and the betas. So the sum of the alphas has to be 0. So the other coefficients from this nasty Taylor expansion, which I use ck in the book, so I'll stick with that here. So it's 1 over k factorial sum from 1 to m. That should be a... Okay, yeah, that's a j. J to the k alpha j. Okay. So for C0, we just have the alphas. But here we have powers of the index j times the alphas. And then we have a second sum involving the betas. J equals 0 to m. J to the k minus 1, beta j. And this holds for k is equal to 1, 2, etc. Okay. So, once you have these, So the multi-step method has error order h to the p if and only if C0, C1, C2, and so on, all the way up to C sub p, all have to they all have to equal 0. So that's how you check. And actually, for the PhD level numerical analysis class, it's Math 772. I use this as a comprehensive exam question. I give a specific multi-step method, and they have to actually work out these coefficients and find out how many of these are satisfied to see what the order of accuracy is.
That sounds terrible.
Yeah.
So, and this is called a
And-
hint. Let's get used to it now because we'll be doing it later.
Not in this class.
No, not
But
in this
yeah,
class, but eventually.
Yeah, if you take 772, yeah. And no cheat sheet. So
Well, cheat sheets are overrated anyway.
there's no one in this room that agrees with you.
Absolutely no one.
That includes him.
Okay, no one else in this room, as in not even me.
Sam, like you. You're also against him.
Yeah. Okay. All right. Well, we'll see then. Okay. And also, I made the method 4-quarter accurate, so I allowed them to check. Okay. Now, once you find the first one of these that is non-zero, then that tells you what the local truncation error is. So the local truncation error is C sub p plus 1. So the first one is non-zero times h to the p power, so that's the order of accuracy. And then there's some more gobbledygook in here. Say minus 1 to the p times the sum of all the betas, which for many methods is 1, but not necessarily. So I have to include it. And then there's also the p plus first derivative of the solution at some unknown point. And then there may be other terms that are of a higher power in h, but we don't really care about those so much. Let's see. No. By making this an unknown point, I don't have to include this. Okay. Or I could say this derivative at time tn plus 1, and then I would have some extra garbage. So that's the local truncation error. So however many of these are equal to 0, that tells you what the order of accuracy is for any multistep method. But at least for Adams methods, it's not necessary. For BDFs, we know what the order of accuracy of a BDF method is. If it's m steps, it's m order accuracy. And that would be worked out in a similar way for Adams methods. I just won't do that here. Okay. So for multi-step methods, because they all have a sort of very restrictive form, there's a lot we can do to figure out what their accuracy is. But one point I want to make about this formula is people tend to focus on this part. What is the power of h? Is it first order, second order, or fourth order accurate, or whatever? And yes, it is very important, but they tend to neglect this part. Because what if this is large? In other words, what if you have a solution, what if your exact solution has a very rapidly decaying exponential that has a term like e to the minus 100t? Well, that function is very small for most t. Like it decays to 0 so rapidly you think, oh, I can ignore it. But you can't, because the derivatives of a function like that are enormous, because you're multiplying by, in that case, minus 100 every time you differentiate. So that could actually be the significant part of the error. And this gets to what is called stiff equations, which, if time permits, which I'm not sure if it will, I'll be able to say a little more about. Okay, so that's the consistency story on multi-step methods. That there's a way to figure out from the given formula and a lot of Taylor expansion what the error during a single time step looks like. And this it's just unfortunate that, in spite of what I've written here in the board, I do not have enough time to convey to you just how ugly it gets. But then it all condenses into a nice result in the end. It just takes so much work to get there. Now that's consistency, but we also have the other half of this, stability, which fortunately is not so ugly to talk about. Okay. So when is a multi-step method stable? So how can we ensure that a small change in the initial data would not lead to a large change in the solution? For that we use the simplest differential equation of all. Y prime is equal to 0. And you have an initial condition that y of t naught is equal to y naught. Now, what is the exact solution of this differential equation? If the derivative of 0, then y is,
A constant.
yes. Which constant?
The first one. 0.
No?
1.
Yeah, why not? The initial value. Yeah, so y of t is equivalent to y naught for all time. Okay. Now, so suppose we apply a given multi-step method to this trivial equation. Well, we'd only have the left side. We have a combination of alphas and y and, oh jeez, dang it. I just realized I goofed earlier. No problem, easily fixed as long as okay, yep. Sorry, fix your notes up here. It's not yi, n plus 1 minus i. And same over here. That's the general form of the multi-step method.
Show that in your video.
Yeah. Okay. Okay. See? That's what a multi-step method looks like. Above my head, right there. Yes. That's in. That. Okay. But again, if I didn't see it after telling him it's above my head, then all hope is lost.
All right, Dana.
Okay. Now, so we only have the left side, which is now written correctly, equal to 0, because f is 0. So your numerical solution satisfies this. So this is called a m plus 1 term recurrence relation. Now, recurrence relations come in handy many situations because you can figure out at least what the solution looks like and get a lot of insight from that. I remember spending a Cal 3 class using a recurrence relation like this showing how you could use geometric series to come up with a formula for Fibonacci numbers. Now, students hated it, but yeah, well, I should have known better, but maybe only graduate students would appreciate something like that. But it's an actual application of material that they were suffering with. So here, so using the theory of recurrence relations, and I wish I could take the time to derive that, but it would be just as painful for most of you as for those undergrads. I'll just jump to the conclusion here that each solution value yn has this form. I'll make sure I keep my notation consistent. Where'd it go? Okay. Nope, not there. Okay, so it has this form of certain constants times certain values lambda raised to the nth power times n raised to certain powers as well. Okay, so I need to explain where all of these come from. Now, the CIs are just some constants in a coefficients in a linear combination, so we don't really care about those so much. But each of these lambdas is a root of a polynomial that comes directly from the alphas. So it's this polynomial, alpha 0, lambda to the m plus alpha 1, lambda m minus 1, alpha 2, lambda m minus 2, and so forth, all the way down to alpha m minus 1, lambda plus alpha m equals 0. So we have a nth degree polynomial equation where we get the coefficients right off a multistep method. So for that, we can go ahead and find the m roots, and these exponents here that n is raised to, that comes from a multiplicity of the roots, lambda I. So in other words, if all of the roots are distinct, then all these exponents will be 0. So they range from 0 up to the multiplicity minus 1. So only if you have repeated roots are you actually going to have anything from that. And this polynomial is called the characteristic polynomial of the multistep method. Okay. So in fact, this equation with the equals 0 included, it's called the characteristic equation. Okay. Although, unfortunately, the term characteristic equation is used in other contexts, like it comes up in DE. It's related, but doesn't quite mean the same thing. So it's a very overused term. Okay, so now that we know that our numerical solution looks like this, we can arrive at a stability condition because the exact solution is constant. Therefore, the numerical solution, it may not be constant. We allow for some error, but it should definitely not grow over time. So for instance, like these roots, these lambdas, they can't be, like if you have a root that is equal to 2, for instance, that's going to grow exponentially. So that's not allowed. So to make sure that the solution, the numerical solution, does not grow, we have what is called a root condition. Okay. So here's the root condition. It actually comes in 2 parts. The first part is all of the roots, lambda I, has to be less than or equal to 1 in absolute value. So if it's a complex number, the roots can be complex. So it can't have a modulus or magnitude that's greater than 1 in the complex plane. Now, but that alone is not enough. If the absolute value is equal to 1, it has to be what is called a simple root. Now, I mentioned simple roots before with root finding methods. In other words, it cannot be a multiple root, like double or triple root. So in other words, the multiplicity must be equal to 1. Because otherwise you have some of those factors of n slipping in there that will lead to exponential growth. Now, if a root is less than 1 in absolute value, it can repeat. It's okay, because that exponential decay will overwhelm everything. So if your alphas in your multi-step method satisfy these conditions, then you're good. Your method is stable. Okay. Now, the thing is, I've not actually shown how this root condition, or even yn not growing over time, ensures that the multi-step method is stable in general for whatever ODE is applied to. That would be an incredibly nasty proof. I've seen it. It's awful. It goes on for pages and pages. So the point is, somebody worked it out way back in the 60s. We're not touching it.
For daily ones.
Well, how can you possibly learn it without proving it yourself?
Go read Isaacson and Keller. You'll find it there. So, yeah. Well, I already told you what a good book that is.
Yes, you
so.
did. You
Yeah.
did. And I actually found a PDF.
Yeah. Oh, good. Yeah. Pretty much all the numerical analysis secrets are in there. Now, if I focus on a particular kind of multi-step method, though, we can make a pretty sweeping conclusion about it. So Adams methods. Oh, actually, before I do that, even when you ensure that the root condition is satisfied, there's two kinds of stability. They're called strongly stable and weakly stable. Okay, so strongly stable is that the absolute value of lambda I is not equal to 1 unless lambda I is itself equal to 1. I should mention, 1 is always a root. Because what does that mean? That means that the sum of the alphas is 0, which has to be true for a method to be consistent in the first place. So you always have that. But if that's the only root that sits on the unit circle in the complex plane, then we say that it's strongly stable. So whereas a method is weakly stable, so if you have a root that is not equal to 1, but its absolute value is equal to 1. For example, minus 1. If that is a root of your characteristic equation, then the method is weakly stable. Or complex roots like plus or minus I, because those have a magnitude of 1, but they're not equal to 1. Okay. Now, okay, so that's the deal on the root condition in general. But now, I'm going to focus on Adams methods. Because of Adams methods, they all have the same alphas, and only 2 of them are non-zero. So in that case, we can easily see what the characteristic equation is. Let's see. Oh, I erased. Never mind.
Will survive.
Well, I can say everything else. It's in the book. So for Adams methods, regardless of whether they're implicit or explicit, you have alpha 0 is equal to 1, alpha 1 is minus 1, and all other alphas are 0. So what that means is a characteristic equation is lambda to the m minus lambda to the m minus 1 is equal to 0. There are no other terms. Now, well, we can factor this. So factor out lambda to the m minus 1, lambda minus 1 is equal to 0. So what are her roots?
0.
And what?
And 1.
1. Yeah, 1 from here. Did you say 2? Oh, okay. I'm sorry. I thought you were being a smartass and saying 2. Okay. What? Okay. Yeah. Okay. Okay. All right. Yeah. So 0 and 1 are her roots. Now 0 is a multiple root, but we don't care if a root that is less than 1 in magnitude is multiple. But so this is the only root that's on the unit circle in the complex plane, and that is a simple root. It only occurs once as a root of the characteristic equation. So all Adams methods are strongly stable. And we know they're consistent. So all Adams methods are convergent. And we know what their order of accuracy is depending on whether it's implicit or explicit. BDFs, the backward differentiation formulas, that's a different story. If I think it's like if m is greater than 6 or something, they're unstable. So lower order BDFs are very commonly used. They play a role in some of MATLAB's ODE solvers, but you can't go to arbitrarily high order with those, unfortunately. Okay. As another example about stability, so this is a method that is neither an Adams method nor a BDF. Make sure I'm writing it down correctly. Okay, so it's an implicit method, and it's a two-step method. So because we go back to n minus 1, any method that goes back to time tn minus 1 is a two-step method, if that's where it stops. If it goes to like n minus 2, it's a three-step method, and so forth. So here we have yn minus 1 rather than yn. If it was yn, it would be an Adams method, but it's not. And this is called Simpsons Method. And the reason why it's called Simpsons Method is that this is based on Simpson's rule for numerical integration. Notice that the midpoint is given 4 times as much weight as the others. So the idea is that this approximates the integral from tn minus 1 to tn plus 1 of f. And that approximation is carried out using Simpson's rule. So that's where the method gets its name. Now, what's unusual about this method is it's a two-step method, but it's 4th order accurate. That's quite unusual because usually, like for an Adams method, if it's an m-step method, its order of accuracy is m or m plus 1. You don't normally have the order of accuracy exceeding the number of steps by that much. But there's a drawback to this method because the characteristic equation is it's a two-step method, so it's a quadratic. So it's lambda squared minus 1 is equal to 0. Because in general, it's alpha 0 lambda squared plus alpha 1 lambda plus alpha 2 is equal to 0 for a general two-step method. And here we have alpha 0 is equal to 1, the coefficient of yn plus 1. The coefficient of yn minus 1 is alpha 2. That's equal to minus 1. Because normally you have all the alphas on the left side. What are the roots of a characteristic equation? You know how to factor viz. So after you teach college algebra or tutor for it.
You got lambda plus 1 and lambda minus 1, so plus or minus 1.
Yes.
Or I could have just done the square root property, which you know whatever.
Well, that too. Yeah. Plus or minus 1. I was going to flash back to Math 500, which is ironic because you didn't have to take that. Okay. So there are two roots on the unit circle, plus or minus 1. So this method is weakly stable because of that root of minus 1. So while it's a very good method in terms of local truncation error being h to the fourth, because of a weak stability, it's a method that's not very popular compared to other multi-step methods. Okay. All right, so that's the deal with stability for multi-step methods. It all boils down to the root condition. Okay. Now, we have 13 minutes left. One thing I want to check on, for those of you who want to subject yourself to it, are whatever problems are given for homework 8, unless you're all going to tell me that no one is doing homework 8. So there's a few problems, well, there's 3 problems from a multi-step method section, and then the rest of them are from this convergence analysis section. Okay, so what I'm going to talk about is, okay, from 12.3, I assigned problems 3, 4, and 5. Well, 3 is an on-paper question. 4 and 5 are MATLAB questions. Okay, so instead of working this into a hints document, I can talk a little about it here. Yes, I suppose it's an invitation for half a class to tune me out. But
So, Nathan's been complaining about it.
what?
Our apartment smells like marijuana and cigarettes. Girl.
Something's been bad.
Oh!
Okay. So this problem, 12.3.4, is to implement a fourth order, which is also the same as a four-step, Adams-Bashforth method. Now, the actual method, like the coefficients, those are given in the book. So in the problem, I point to the equation number. Okay, so it's yn plus 1 is equal to yn plus h over 24, 55 fn minus 59 fn minus 1 plus 37 fn minus 2 minus 9 fn minus 3. Okay. Also, you need starting values. That's one drawback of multi-step methods in general. And for that, you use fourth order Runge-Kutta method for that. So your function, if I give you like an outline of it, we have a vector of t values and a vector of solution values of, okay, and I call the function Adams Bashforth 4 with arguments f, t span, y naught, and h. Okay. Well, first you need the initial and final time values. So like your t naught would be the first element of t span. And then the final time, I'll call it tf, is the second element of t span. And I just do that just because this is how MATLAB's ODE solvers, they work with a similar kind of syntax. So what you can do, if you have a four-folder run and cutoff function, which comes from a previous problem, you can go ahead and call that. And it takes the same arguments. But what you would do is, for a four-step multi-step method, you need 3 starting values. So you have y naught already. You need y1, y2, and y3. So what you could do is you could use a different t-span. Start with your initial time, and you're only going to take 3 time steps. So t naught plus 3h, because that's going to take 3 time steps. Okay. And then same initial data, same h. So that gives you the starting values. And what will happen is, so this gives you a vector, well, t0, t1, t2, t3, and also y naught, y1, y2, and y3. So those are the 2 vectors that will come out of this call to RK4, which comes from that's from previous assignment from homework 6. Okay, that's a semicolon right there, believe it or not. Okay, I have 7 minutes. Now, what you can do after that is okay. You need to plug in, you need to keep track of f values also, because right now you don't have any of them. But what you can do is, in a loop, you can make a vector of f values where you plug in your t values and your y values into f. So then you'll have those available for when you use a multi-step method coming up next. So you do that in a for loop for the 4 values that you have. So that's what gets plugged into there. Okay. Now, so what you would do after that, and also work that in over here, is you need to keep track of what time step you're currently on, because you've just computed y0, y1, y2, y3. The next thing you're going to compute is y4. So, in other words, you're going to start with n equal to 3 to compute y4. So you might as well keep track of that. N is equal to 3. Now, what are the maximum number of time steps you're going to take? So I can keep track of like n max. That would be equal to the final time minus the initial time divided by h. Although you want to round this. There's a MATLAB function called round, so it'll round that to an integer. So really you would say like round parentheses this. So I forgot to include that in there. But So that tells you here's how many time steps it's going to take. So then you can have a loop. And that would go from well, okay, I shouldn't call this n. I'll call this n star. Okay. So n star up to n max minus 1. The reason for the minus 1 is you want your final value at your last time step, this to be n max. That's n plus 1. So these will be the n values that actually get used in here. So then this formula can be used right in here. And these, n plus 1, n minus 1, n minus 2, n minus 3, those are indices into your f vectors and your y vectors. So really, this is all you do in there. In fact, I might have given too much of this away, but that's okay. I'm fine with that. And that, just like in the other problems where time-stepping methods are implemented, you keep accumulating your solution values. Like here, you have your vectors t and y that contain your starting values, but you need to concatenate onto these vectors the additional values you'll get from that loop. Okay, so I'll leave that part to you. But you have a framework now. Dang it. Where's Teresa?
It's still recording though.
Well, yeah, but I need to make sure it's actually seeing all this. Because I went over there and I can't tell what it's seeing. Well, I shouldn't be doing that. Okay, well, I have 3 minutes left. Dang it. Okay. Well, while I'm waiting for her to reappear, okay, the other problem I gave in this section, number 5, predictor corrector, which so they're using 2 multi-step methods in combination, but once you have this number 4 done, then it will work in a very similar manner. Okay, so, all right, well actually I think I've written on the board all I need to, but I just need to make sure. I don't care. Sorry, I just texted her to get back here. Okay.
Can't go to the bathroom.
Okay.
8 people blowing up my phone.
Yes, timing is impeccable. Okay, so now I'll make sure that I have all of this. Okay, so what I was working out at first, which I think I got previously, and then the rest of a function, okay, a framework for it right here. But basically, your loop is going to consist of this formula and storage of all the t and y values which are happening in all the problems that involve implementing a time-stepping method. Of course, I, again, can't fume about this enough, how few questions I get on these coding problems. I've gotten some, it's increased a little bit, but not nearly enough. And then what I get turned in is not snuff. It's like, well, if you had sought help from me earlier, then this could have been avoided. So you guys failing to ask questions just breaks down the whole mechanism of class. So these last couple weeks, knock that off. So, good undermining me. Okay, so this is actually all I have on initial value problems. On Thursday, I will cover one section of boundary value problems, which actually use some of this stuff. And then Amber will swoop in next Tuesday to finish covering that. Okay. Oh, Amber Sumner will be co-author of a textbook, who's going to be the substitute on Tuesday. Okay.